Okay, let's start by question number 1. Okay, what do we have now? A 5mm thick copper plate is sealed to a 10mm thick aluminum plate, and both have the same cross-sectional area of 1 meter per 1 meter squared. Okay, so now we are talking about two different metal, which is copper and aluminium, with two different thickness, which is 5mm and 10mm each of them, but the cross-sectional area is still the same, which is 1 meter squared. Okay, the outside face of the copper plate is at 100 degrees Celsius, while the outside face of the aluminium plate is 80 degrees Celsius. So the temperature at the outer part of the copper is 100 degrees Celsius, while the temperature at the outer part of the aluminium is 80 degrees Celsius. So they ask you to find the temperature, okay, in between copper and aluminium interface. Okay, so we are talking about the temperature, okay, at the middle between these two material, and then calculate the rate of heat flow through the cross-sectional area if heat flow is steady and no energy is lost to surrounding. Okay, the keyword is at steady state. So remember, at any steady state, the condition is dq over dt still remain constant or uniform. Okay, so the thermal conductivity given for copper, also aluminium. All right, so we just simplified the question. So what do we have? Okay, we just pointed out all the info given. So this is the thickness of copper, this is the thickness of aluminium. We just convert it to be in meter. All right, and then the area of copper and aluminium still the same, which is 1 meter squared. The temperature at the outer part of the copper and the aluminium is given too. All right, so we may sketch a simple diagram to be like this. Okay, so this is the copper side, and this is the aluminium side. Okay, where the thickness of copper and aluminium given already, and the temperature at the outer part of the copper is 100 degrees Celsius, while the temperature at the outer part of the aluminium here is 80 degrees Celsius. So they ask you to find the temperature at the interface between copper and aluminium, in between 80 to 100 degrees Celsius. So what is the temperature here, which is T here? All right, so they ask you to find this T. Okay, so to find the temperature, okay, at the interface between copper and aluminium, so remember at steady state, the rate of heat flow, okay, which is dq over dt in copper and aluminium, they are the same. Okay, so for copper, dq over dt equals to ka dt over dx of copper, and for aluminium, dq over dt equals to negative ka dt over dx of aluminium. All right, so this is thermal conductivity of copper, and this is the cross-sectional area of copper. This is the temperature difference in copper. Okay, and then the thickness of copper, still the same for the aluminium, thermal conductivity, cross-sectional area, temperature difference, and the thickness of aluminium. Okay, so the temperature difference in copper, so in copper should be T minus T of copper. And remember, dt should be negative. Why? Because we got negative here. The temperature gradient is negative, so it must be cooler temperature minus the higher one, isn't it? The cooler one should be at the interface lah. So T minus T copper. All right, and then we just do the same thing for the aluminium. Okay, so this is the thermal conductivity of the aluminium, cross-sectional area of aluminium, and this is the temperature difference in aluminium. So in aluminium, should be T of aluminium minus T at the interface lah. And because 80 is smaller or lower than this temperature, isn't it? This is 80, we got something here, and then 100. So 80 minus something here lah. Okay, so 80 minus, okay, T aluminium minus T at interface. Okay. Alright, so we just substitute all the values. This is thermal conductivity of the copper given already. This is the thermal conductivity of the aluminium given already. Okay, so this is unknown T minus T copper, which is 100. And then the thickness of copper is 5 millimeters, convert to be in meter. Okay, and then for aluminium, still the same. The temperature difference now is 80 minus T, and then the thickness of the aluminum given is 10 millimeters, converted to be in meter again. So mathematically, we may simplify all the calculation to be like this. At last, you will get the temperature at the interface now, or at the boundary between copper and aluminium is 96 degrees Celsius. See, 80, 96 and 100. It just obey the principle lah. Okay, where the temperature is greater than 80 but smaller than 100, isn't it? Because T just in between copper and aluminium. Alright, and then for the second question, they ask you to calculate the rate of heat flow through the cross-sectional area if heat flow is steady and not energy. Okay, now they ask you to find the rate of heat flow, dQ over dt. So remember, dQ over dt in copper and aluminium, they are the same. So we may use the copper one or the aluminium one. And the answer is getting now still the same because we are talking about the steady state, where dQ over dt just the same. Okay, alright, so using the copper part, so dQ over dt equals to negative Ka dt over dx in copper. Alright, so we are talking about thermal conductivity of copper, which is 400, and given already. The cross-sectional area is 1 meter squared. Okay, and then T calculated just now is 96, so 96 minus 100, we just refer to the temperature in copper. Okay, and then the thickness of copper is 5 millimeters, converted to be in meter, so that you will get this answer. Or by referring to the aluminium part, okay, so dQ over dt equals to negative Ka dt over dx in aluminium. Alright, so thermal conductivity of aluminium given is 200. Cross-section area is still the same, which is 1 meter squared. So the temperature difference now is 80 minus T calculated just now, which is 96. Okay, and then the thickness of aluminium given already, which is 10 millimeters, converted to be in meter. Then you will get the same answer as before. Okay, you may choose one of it enough. Okay, we don't have to use two different these two equations, just one of it lah. Okay. Okay, let's continue by question number 2. Okay, this is question number 2. What do we have? Okay, the rate of, okay, we just start by 2A. The rate of heat conduction is 80 kilojoule per hour. See, kilojoule per hour. It's not in SI unit. We got prefix here, which is kilo, also per hour. Alright. At a thin wall with an area of 14 centimeters squared. So this is the area. If the temperature gradient across the wall is 15 degrees Celsius per meter, calculate the thermal conductivity of the wall. Okay, what do we have now? So this is the rate of heat conduction, which is dQ over dt. But it's not per second, it's just per hour. So dQ over dt given out is 80 kilojoule per hour. Alright, and then this is the cross-sectional area, which is 14 centimeters squared. So we just convert it to be in SI unit, which is meter squared. Centi is negative 2 times 2, you will get negative 4. Okay, and then this is temperature gradient, which is 15 degrees Celsius per meter. So remember, the temperature gradient always negative. Okay, alright, so now we need to convert this to be in SI unit. It must be in joule per second. Okay, so the thermal conductivity, okay, now we just refer to dQ over dt. dQ over dt is 80 kilo. 80 kilo is 10 to the power of 3, for kilo. And then per hour, okay, so in 1 hour, we have 3,600 seconds. So we just total up the values here. You will get 22.22 joule per second. Okay, so we just convert the values given now, which is in per hour, to be in per second. Okay, so by getting the value of dQ over dt here, by using the same equation, the rate of heat flow, which is dQ over dt, equals to negative Ka dt over dx. So by rearrange the equations, you will get the thermal conductivity, because they ask you to calculate the thermal conductivity, isn't it? K. So by rearrange the equations, you will get K equals to negative dQ over dt divided by A dt over dx. So dQ over dt calculated before is 22.22. Okay, we got negative here. Why? Because we got the negative sign in that equation, isn't it? Okay, and then the area is 14 exponent times 10 to the power of negative 4. And the temperature gradient is negative. See, it's very important. Why? Because negative and negative, they will cancel. They are cancelling each other. Okay, so giving you positive answers here, which is K equals to 1058.1 watt per meter per degree Celsius. Okay, it's very important. We need to know that the temperature gradient always in negative. Why? To cancel out the negative sign in that equation, because the negative sign actually representing the temperature gradient. Okay, all right, then you will get this answer. Okay, next for question number 2B. Okay, it's quite interesting because you need to know actually. Okay, actually the diagram should be given because without the diagram we cannot answer the question. Okay, all right, so for question number 2B, what do we have? An electric bulb or menthol rated at 80 watt 240 volt has inside it a heating filament. Each end of the filament is connected to a supporting straight wire diameter of 1 mm and length 4 cm. So this is the bulb and this is the filament and this is our supporting wire. We have two supporting wire here. Okay, and then the diameter of the supporting wire given is 1 mm and the length of the supporting wire is 4 cm based on this question. When the bulb is switched on and functioning at the given rating, the filament temperature is 1000 degrees Celsius. Okay, so for this supporting wire, the end of the wire now which is connected to the filament, the temperature is 1000 degrees Celsius. Okay, while the temperature at other end of each supporting wire is 60. At other ends now the temperature is 60 degrees. Okay, so remember the filament is very, very hot, isn't it? That is why the first end here the temperature is higher, which is 1000 degrees Celsius, while the other ends is at 60 degrees Celsius only. Okay, so estimate the ratio of power loss to the thermal conduction of heat away from the filament along the supporting wire to the power supply to the filament. Okay, so thermal conductivity of the material of supporting wire. Okay, so K of this supporting wire given already. K given, which is 59 watt per meter per Kelvin. Okay, what do we have now? So again, by pointing out all the info, power given is 80 watt, and then this is the voltage supplied, which is 240 volt. All right, so remember by having this, so remember for any label, it just represent you the power supply and voltage supply, isn't it? So this is power supply actually. This is power supply. Okay, so now they ask you, okay, by giving, okay, and then everything given here already, the diameter of the supporting wire, also its length, and the temperature at the first end here, which is nearer to the filament, and then the temperature at the other end here, which is 60 degrees Celsius. Okay, they ask you to find the ratio of power loss to the power supply. So remember, this is the power supply, according to the voltage supply. So for any label, that one is the maximum values can be supplied to the electric instrument. Okay, all right. So to calculate the power loss, the ratio of power loss to the power supply. Okay, so remember for any wire, normally the cross-sectional area is pi d squared over 4. And okay, P supply given already, which is here 80 watt. But what is P loss actually? Okay, P loss actually still the same with the rate of heat flow through the supporting wire. Because you can see that the temperature are different, then we are talking about the heat flow. So the rate of heat flow actually representing your power. So remember, power is the rate of energy or the rate of work, isn't it? So the rate of heat flow also representing you the power loss. So in this case, we need to find dq over dt by these two supporting wire. Okay, so again, by using the equation of dq over dt equals to negative ka dt over dx. Okay, so this is the equation of dq over dt, or the rate of heat flow through the supporting wire here. All right, k given already, which is 59. Area is pi d squared over 4, so pi d squared over 4. All right. The temperature different now, remember, should be cooler area minus the higher one, isn't it? So 60 minus 1000. 60 minus 1000, that one is temperature different. And then the thickness here, actually I'm representing your length, the length of the supporting wire is 4 centimeter. So 4 centimeter equals to 0.04 meters. So by calculating this, you will get dq over dt through this supporting wire is 1.09 watts. That one for one supporting wire. But now we have two supporting wires here. Okay, so we just multiply by 2 lah. So 1.09 watts times 2 giving you 2.18 watts. So this is the power loss by these two supporting wire. So by getting this, substitute into this equation, this is the power loss by that two supporting wire, and the power supply is 80. So the ratio now you will get 0.027. Okay. Alright, so how do we know that there are two supporting wires here? Okay, this is the keyword. Each end of the filament is connected to a supporting straight wire. Okay, end of filament. So we have two ends. The first end, the second end, isn't it? The first end connected to the first supporting wire. The second end connected to our second supporting wire. So there are two supporting wires actually. That's why we need to calculate the power loss by two wires. Okay. So remember, this is the way how to calculate it. Okay, but normally for the exam, for any case to be like this, the diagram should be given, because we need to know how many supporting wires do we have, because it's quite tricky here according to the sentence. Okay, that's all. Thank you.